Lewis dot diagrams. But in order to do that, we need to review valence electrons. So remember, the periodic table is very helpful because it shows us how many valence electrons elements have. So if you're in group 1, your alkali metals and hydrogen, you have 1 valence electron. If you're with your alkaline earth metals, you have 2. Then we're going to skip over the transition metals and to the group with boron, that would be 3, 4, 5, 6, 7, and 8 valence electrons. However, what happens if you have a trickier one? So for example, what if you have a transition metal? So let's look, for example, at zinc. Okay? I'm going to really quickly write out the shorthand electron configuration for zinc. So keep in mind, to write the shorthand electron configuration, you're going to move up a group, you're going to move up a row across to the noble gas, which would be argon, and you're going to put that in brackets, and then you're going to keep reading. So I go down to where potassium is, that would be 4s2, and then 3d10. So looking at this and remembering that valence electrons are the electrons in the outermost energy level, this tells me that zinc, because 4 is the highest energy level there, has 2 valence electrons. So those are the trickier ones. It's still not that tricky, it's just that you can't count using the periodic table. So zinc has 2 valence electrons. So you're going to complete the rest of the problems that I gave you, and then we're going to move on. So you're going to learn in this video how to create Lewis dot diagrams. So there are specific steps that you need to take to make sure that you're doing it correctly. And the steps are CSLC. So let's look at each of these. So C stands for count the number of valence electrons. So we'll look at that in just 1 second. Next, you're going to share electrons between elements. Then you're going to add lone pairs to the outer elements and then to the central element, and we'll look at that. And then you're going to count the number of electrons used, and that needs to match with the number of valence electrons. If it doesn't, then we have to problem solve, and so we'll get to that in class.
So I'm going to show you how to draw the Lewis dot diagram for water and for phosphorus tribromide. And I'm first going to show you how to draw it without the model kit. Then I'll show you with the actual physical model kits that you guys will have in class. And then using that, I will then draw it properly, okay? So if I look at this, I have water, so I have H2O. So remember, my first step is that I need to count my number of valence electrons. So hydrogen each have 1, so I'm going to do 1 times 2. And oxygen has 6, so that's a total of 8 valence electrons. My next step is to have those atoms share electrons. So oxygen's going to be at the center because I only have 1 of them, and I'm going to have it share electrons with hydrogen. Okay. My next step is to add lone electrons. So remember, every atom on the periodic table, except for hydrogen and helium, want 8 valence electrons. Okay? So hydrogen right now, because I have this bond right here, this bond represents 2 electrons. So hydrogen sharing 2 with oxygen, so each hydrogen right now has 2 already, so it's happy. So it's not going to want more electrons, so I'm not going to put any lone electrons on this guy. But oxygen right now only has 4 electrons total, so I need to add 4 more. So I'm going to add 2 more pairs, so 1 pair there and 1 pair there. Okay, so now oxygen has 8 electrons. Now I need to count again because remember, I need to use 8 valence electrons. So right now I'm using 2, 4, 6, 8 electrons, which is how many electrons I should be using. So this is a perfectly fine Lewis diagram, but now let's look at it using the model kit.
So if I'm going to create my first molecule, okay, if I'm going to create water, here's my oxygen atom. Now notice it has 4 holes in it, so there are 4 possible different slots for it. So I'm going to put 1 hydrogen here, and it doesn't matter where you put the other hydrogen at all. You can put it in whichever slot you want to be able to put it in, okay? So this is the correct model for water. Notice I've got those 2 holes on top which represent the lone pairs of electrons. So looking at this, I'm now going to draw it properly on paper.
So using the model kit, as you noticed, your oxygen's going to be here, but because of your VSEPR model, which states that atoms are going to be located in such a position to minimize the repulsive forces of electrons. Okay? My oxygen is going to be here. My hydrogens are going to be like this. Or you could totally flip it and have it up above, but I tend to draw it like this. And then the lone pairs of electrons, which on that model kit are represented with those empty holes, your lone electrons are going to be up here. Okay? So while this is correct in the sense that I have the correct number of electrons, this is the correct structure, and this is how you would need to draw it on a quiz or test. So you will always have your model kit available so that you can draw it properly. At a certain point, you're going to get so used to doing this that you're not going to need your model kit. But just as a quick review of the VSEPR model, why this is correct but this one isn't. Remember, your electrons are going to repel the atoms. So they're going to force them downwards. And so in order to minimize that repulsive force of the electrons pushing down on that hydrogen atom, your hydrogen atoms are going to be here versus here because they're going to be pushed downwards. Okay? So let's look at another example. We've got PBr3. So for PBr3, I've got to first count my total number of electrons. So for phosphorus, I have 5 valence electrons. For bromine, I have 7, so it's going to be 7 times 3, so I'm going to have a total of 26 valence electrons. So if I draw this without thinking about my VSEPR model, I'm just going to share electrons. So I have 1, 2, 3 bromines coming off of this. Remember, every atom, except for your hydrogen and helium, need 8 valence electrons. So right now, this bromine only has 2, so I'm going to add 6. I'm going to add 6. And I'm going to add 6. Then, phosphorus right now has 2, 4, 6, so it needs 2 more. Okay? Now let's look at it using the model kit. For PBr3, I'm going to take my phosphorus. I'm going to take this black ball again. Okay? Remember, you've got 4 different possible places to place your atoms. Okay? I'm going to put 1 here. Okay, so 1 bromine there. 1 bromine there, and then finally 1 bromine there. Okay, so if you look at this, notice you've got 1 lone pair of electrons here, which we're going to represent in a second, but the way we're going to draw this is with it moving downwards, downwards, and downwards to try and show that 3D shape. Because notice it isn't flat. If you drew 1 up, 1 down, that would imply that this was flat, but notice it's not. So we're going to go downwards, downwards, downwards for drawing. So let me show you that. So based on the model kit, phosphorus is going to be in the center. It's going to have 3 bromines, and they're going to be forced downwards like this, because you then have your lone pair of electrons on top. Now, I'm going to stop drawing the 2 dots simply because it takes more work. Instead of drawing the 2 dots, you can simply draw 1 line, and that represents 2 electrons. Okay? Then I need to add my 6 electrons, so I'm going to add 2, 4, 6, 2, 4, 6, 2, 4, 6, and that is the proper structure for PBr3, the Lewis dot structure, taking into consideration your VSEPR model. These are trickier Lewis dot structures. So let's look, for example, at oxygen. And the important thing for you to know when you're doing these is you really need to follow these steps, or else you're going to end up getting the easier Lewis structures wrong because you're going to end up confusing yourself. So really make sure you're paying attention. So if I give you O2, remember your first step is to determine the number of valence electrons. So that would be 2 times 6, which gives me 12. Okay. My next step, again, remember we're going to share electrons. Okay. And I'm going to add my lone electron, so everyone has 8 valence electrons. And now I'm going to count. Okay, so let's count. So I have 2, 4, 6, 8, 10, 12, 14 electrons I'm using, but I only should be using 12. This is the only point where once you've filled in your Lewis structure and you realize you're using too many valence electrons, this is the only point where you should do what I'm about to do. If it works, right, always do it. Check if you have the correct number of valence electrons. Do not do what I'm about to do. Only if you're using too many valence electrons, which I am right now. I'm using 14. I need, instead of just using one bond, I need to have oxygens share another pair of electrons, because if you look, if they now share 2 pairs, that means both oxygens have 4 electrons right now. So I'm going to add 2 more, so that's 8 electrons total. So now I'm using 2, 4, 6, 8, 10, 12 valence electrons, which is how many I want to use. Okay? So only in a situation where you've filled out the Lewis structure, you're using too many valence electrons in order to make sure everyone has that perfect octet, only then should you use a double bond. And as a hint, eventually you might also have to use a triple bond, but only use a triple bond if I filled this out, I was still using too many valence electrons. Do not just blindly add triple bonds. That's what a lot of students like to do. Start off with the same steps that we did before. When you do your final count, if it doesn't work, then you can try a double bond. Okay, so let's look at one more example. If I gave you SO2, okay, so let's figure out valence electrons. So sulfur has 6 valence electrons. Oxygen has 6 as well, but there are 2 of them, so that's a total of 18 valence electrons. Okay? So I'm going to share electrons, and I automatically draw it like this simply because I'm pretty sure they're going to be lone pairs of electrons here. So I know that that's going to force the oxygens downwards based on your VSEPR model. So I drew it like that. Okay? I'm going to make everyone happy. And then sulfur right now has 2, 4, so I need 6, 8. Okay? So now I need to count. I'm using 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I'm using too many electrons. So now, and only now, can I use a double bond. So I'm going to use a double bond. So I'm going to draw this. I'm going to put the double bond on the left-hand side. And I know the question is going to come up. Just give me one sec. I've got 4 electrons on this oxygen, so I'm going to add 4 more, so 2, 4. I've got 2 electrons here, so I'm going to add 6. And then I have 2, 4, 6 here, so I'm going to add 1 lone pair here. Notice it still is going to have that bent-looking shape simply because I've got that lone pair of electrons here. So I know the question is going to be, well, how do you know where to put the double bond? Well, you don't. So this is an example of what we call resonance. Okay? So what actually exists is not this. I'm going to draw a double arrow to show that this other thing can exist. I'm going to put my double bond on this side. So put it on the opposite side. And the question I'm sure is going to be, do I have to draw both versions of this? The answer is yes. And if we had 3 different ones and just one double bond, you have to draw the double bond on top, bottom, and to the left. So you'd have to draw 3 different versions. Now, this is resonance. And the important thing for you to know is that neither of these actually exist. What actually exists is an average of these 2 molecules. So specifically, if, for example, this were, let's say, yellow, the color yellow, I'm just creating an example to help you understand this, and this were the color blue, what would actually exist for SO2 is not yellow and blue. Instead, what would actually exist is the color green.
So we're going to talk about bond order and how to determine it, and then also how that allows us to talk about the length and the strength of bonds. So to determine bond order, what you do is you count the total number of bonds. Okay? So a single bond counts as 1 bond, a double bond counts as 2 bonds, etc. And then you're going to divide that by the total number of bonding domains. Okay? So for example, if you have CO2, the bond order, I'm going to determine that by saying, okay, I've got a total of 4 bonds there because I've got 2 double bonds. And I'm going to divide that by the total number of bonding domains, which is 2. So 4 divided by 2 is 2. So the bond order is 2, which is pretty easy, and you could have determined that without doing this because a double bond has a bond order of 2. A single bond has a bond order of 1.
So what if you're trying to determine bond order, but you have a case of resonance? So if we look in the case of CO3 2-, we've got 2 single bonds and a double bond. And so what you're going to do is you need to find the average of those bonds, because remember, what exists in that resonance structure is an average of the bonds. So what I'm going to do is I'm going to take each of the bonds, so a single bond, which is a bond order of 1, add to that another single bond, a bond order of 1, plus a bond order of 2 because of the double bond, so 1 plus 1 plus 2, and then I'm going to divide that by the total number of bonding domains that I have, which would be 3. So 1 plus 1 plus 2 is 4, divided by 3 will give me a bond order of 1.33.
Okay. What if instead I have another resonance situation, but now I have just a double bond and a single bond?
Well, I need to average those. So I've got a double bond, so a bond order of 2, plus a single bond, a bond order of 1, so that's 2 plus 1, which is 3, divided by the total number of bonding domains that I have, which is 2. So the average of that would be 1.5. So this makes sense, the 1.33 and 1.5, because if you think about it, if I were to ask you what's the average of 1, 1, and 2, what you would do is you would add up all three of those numbers, 1 plus 2, and you would divide it by the total number of numbers, which is 3. So 4 divided by 3 would give you 1.33. That's the average of those three numbers. Same thing for the other resonance structure. If I said, what's the average of 2 and 1, what you would do is you would take 2 plus 1 and you divide it by the total number of numbers, which is 2. So 3 divided by 2, so the average is 1.5.
Well, why do these numbers matter? Well, these numbers matter because the larger your bond order, the stronger the bond's going to be. So I could have asked a question, for example, which has a stronger bond, carbon dioxide or carbonate, CO3 2-? Well, since, and the way that you explain it, since carbon dioxide has a bond order of 2, while carbonate has a bond order of 1.33, carbon dioxide is going to have a stronger bond. Another thing to note, the larger your bond order, the shorter the bond's going to be. So I could ask, which would have a shorter bond length, carbon dioxide or carbonate? And the answer would be carbon dioxide because it has double bonding. It has a bond order of 2, while carbonate only has a bond order of 1.33.